This video is for ELEC 1510 Logic Design. This is Lecture 11, Part 3 on Behavioral Verilog, corresponding to Textbook Section 4.12. Let's discuss some of the Verilog code types that we've already gone over in this class. The simplest is gate-level logic. Now, if we wanted to design gate-level Verilog for just a simple AND circuit where we're taking an AND function of x and y and producing the variable z at the output, this is what the gate level logic would look like. We declare our inputs x and y, we declare our output z, we declare an AND gate named gate G1, so this gate would technically be gate G1 that has output z and inputs x and y. That's pretty simple, but it's very low level, and once we get into very complex circuitry, it becomes inefficient to write code this way. For the same logical function, AND of x and y producing the output z, a Boolean expression in Verilog can be written as the following code. We declare our inputs x and y, again our output z, and then we assign z to be equal to the AND function of x and y. This is a little bit higher level code and can allow us to design more complex circuitry a little bit easier. An even more higher level code in Verilog is called behavioral expressions. In behavioral Verilog, we use an always statement to declare the variables in the module that can change. So we want to change the outputs whenever these variables change. That would be x or y, which are the inputs. So the statement that we use is always at symbol, parentheses, x or y. So those are the inputs that can change, and we want the output to change whenever one of those inputs changes. Then you can use if statements to describe conditional outputs. So if x and y is equal to 1, that means that both x and y are 1, and we get a 1 at the output, then z is equal to 1. Okay, so there's a lot going on here. Obviously, if x and y are equal to 1, there's an AND statement going on there that produces a 1 at the output, but then that 1 is assigned to the variable z. For other conditions, we would use else or else if statements. So if you only have one other condition, you would use an else statement. If you have multiple conditions that you need to account for, you would use else if statements. You also need to make sure to declare your outputs as output reg, which is a different variable type that we need in behavioral expressions. So the behavioral expression in Verilog for the same logic function, x and y into an AND gate and z at the output of an AND gate, looks like this. We declare our inputs x and y, we declare our output reg to be z, and then we say always at symbol x or y, meaning that x or y can change, and that will produce a change at the output. Then if x and y are equal to 1, z is going to be equal to 1, else z is going to be equal to 0. Okay, so this looks a little bit more like C code. It's still not running through a loop or doing other control structures like that, but it does look a little bit more like C code. All right, so a little more complicated behavioral expression is, let's say that we want to model an exclusive OR gate with inputs x and y and output z. We declare our inputs x and y, we declare our output reg z, and then we say always at symbol x or y. Now we can account for the two combinations that produce a 1 at the output in various ways. I chose just to demonstrate an if statement, an else if statement, and an else statement to break it into two parts. So each part would refer to one minterm. So if not x and y are equal to 1, then z is equal to 1. So that's one of the minterms in the XOR gate that produces a 1 at the output. Then else if x and not y are equal to 1, z is going to be equal to 1. Else, for any other input condition, z is going to be equal to 0. And that's how you model behavioral circuits in Verilog. Behavioral expressions are going to be much more important in the upcoming chapters on sequential circuits.